When you hold your phone up to a speaker in a noisy cafe, Shazam isn't listening to the lyrics or the melody the way a human does. Instead, it converts the audio into a visual representation called a spectrogram. A spectrogram is a three-dimensional graph that plots frequency on one axis and time on the other, with the intensity of the colour representing the volume or energy at that moment. Think of it as a musical map that highlights the exact peaks and valleys of a song's energy. This visual map allows the algorithm to ignore the background chatter of a crowd and focus only on the strongest, most consistent parts of the signal. By simplifying a complex wall of sound into a set of high-energy points, Shazam creates a manageable digital signature that can be analysed in seconds. Processing every single millisecond of a song would be computationally impossible to do in real time across millions of tracks. To solve this, Shazam identifies specific peaks within the spectrogram where the energy is at its highest. These peaks usually correspond to a sharp drum hit, a distinct guitar note, or a powerful vocal moment. The algorithm ignores the lower energy noise and focuses only on these constellation points. However, a single point isn't enough to identify a song, because many songs might share a similar peak at a specific frequency. To create a truly unique identifier, the system looks at pairs of points and the specific time interval between them. This relationship between two frequencies and their distance in time is what forms the basis of an audio fingerprint. This pairing process creates something called a hash. A hash is a compact numerical code that represents an anchor point and a target point within the song's spectrogram. Each hash contains the frequencies of both points and the exact amount of time that passed between them. Because music is repetitive and structured, thousands of these hashes are generated for every 10-second clip. This massive redundancy is the secret to the system's speed and accuracy. Even if your microphone only catches a few seconds of a song through a layer of wind or conversation, the algorithm only needs to find a handful of matching hashes to identify a potential candidate in its massive database. The final challenge is matching your live recording against the millions of songs stored on Shazam's servers. The system doesn't just look for the same hashes, it looks for those hashes appearing in the same relative order and timing. This is done by comparing the time offset of the hashes in your sample to the hashes in the original track. If the peaks in your recording happen at the same relative intervals as a song in the database, a hit is recorded. When a significant number of these hits line up perfectly on a timeline, the algorithm confirms a match with near certainty. This temporal alignment is why the app can identify a song even if you start recording in the middle of a bridge or at the very end of a chorus.